All right, so everybody can see my screen now?
Yep.
Yeah.
All right, so today we're going to start talking about lists. Now, I did already give you a reading assignment I put up today. We'll see if we get to a programming assignment too, but we'll at least have a reading assignment for Friday. So I really want to think about lists from the perspective of the difference between lists and strings. So lists are different from strings in that they are read/write. So up to this point, our pattern has been with strings. Let's see. Yeah, if you just got on, the easiest thing to do is just mute your mic so there's not background noise, and you can, talk to people or whatever. And then if you have a question, just unmute yourself and then yell something out to get my attention. There's also a chat box thing, but it doesn't always pop up letting me know somebody's chatting, so just scream or something to interrupt me. So what I mean by strings are, well, okay, let's go like this. Let's say strings are read only. All right, so what I mean by that is if I have a string S and I say it's equal to hello, I can't go in and say I want S at, I can't say I want to remove the E from S. I would have to build a brand new string, S2, and set it equal to HLLO to get that E out. So our pattern up to this point has been to build a brand new string and then concatenate onto that the things we wanted to keep. Whereas lists allow us to access an individual bucket of a string or of a list. So if I have a list, like this, I can go ahead and I can say L at bucket 1 is equal to a 5. And then what that would do is it would permanently change the value of L at bucket 1 here to a 5. All right, so I'm allowed to go in and change individual values within a list as I go through the list. Now, just a couple of things here. Let me pop open from the book. Some of the basic constructors for lists, for building them conveniently, and we'll kind of walk through a couple of them really quickly. So we've actually jumped ahead to chapter 8 here. These are the methods. No, I actually think I wanted the previous one. I wanted the list building things. Yeah, this guy. All right, so we see the different ways we can create a list. So we can say, like, my list is equal to 1, 2, 3, and that's similar to what I've done here. So let's just start putting these things in. So I can say L is equal to 1, 2, 3. And then if I go and print out L, we'll see that we get that entire list printed out. So there's my list 1, 2, 3. Similarly, I can say I want L at bucket 1. So this is very similar to how we worked with strings, where strings were 0 indexed. So the length of L here is 3. The legal buckets are 0 to the length -1. So this guy would print out the 2. I were to print out the length of L, so we already have been using the length function. This guy takes a collection type as a parameter and gives us the number of elements that are in that collection type. Is there a question? All right. So we also have a constructor for building lists conveniently. Let me show you this. I can say we'll just do it in L2. We can say L2 is equal to the list 1, 2, 3. And we'll print out L2. There's the list 1, 2, 3. But notice that, so I gave it to it as a string, right? And it split that guy up into individual buckets. But notice the type. Those guys are string representations of those numbers.
Are you re-downloading Venus? You can't hear me. I think you can.
Question. Yeah, you can ask a question there.
You should probably see it.
Just in case I don't that somebody should yell and say there was a question in chat. All right, so some patterns we've seen up to this point is we've previously stored like all the numbers, you know, go up to there. We've stored stuff like that, and we can go ahead and get that quickly into a list by using the list constructor. So something like this seems way more convenient than so on and so forth. You know, hard coding it in there. So we have this function called list that allows us to quickly build a list giving a string. And it assumes that your separation is between each element in that string. Okay. So that's the next constructor thing. So this is this list constructor. We already saw how we can get an individual element from the list. We also have the ability to get sub lists. So part of the list. So if I want to get L2 from bucket 3 to bucket 7 non-inclusive, this is 0, 1, 2, 3. So this is bucket 3. This will give me 3, 4, 5, 6, but not the 7. Does it want all these types to match? Oh, I still had my inconvenient way of writing this up here. So I had a forced error up in my first line of code here. But there's my 3, 4, 5, 6. So notice that this guy works similarly to range, where the first value is inclusive and the second value is exclusive. So this says, give me everything from L2 from bucket 3 all the way up to, but not including bucket 7. Okay. We can also glue lists together. So kind of like concatenation. So I can say list L2, then I can say L3 is equal to, I don't know, let's just do 13, 14, 15, something like that. And then I can say L4 is equal to L2 plus L3. So here's L4. It's everything L2 used to be with those other things tacked on to the end. Now notice here that this list has a whole bunch of different types of elements in it. So that's another example of Python being loosely typed. So this guy holds a whole bunch of strings followed by some numbers. So that might not necessarily be something that's all that useful, what we just did there, but you can use the plus operator to concatenate lists together. We can change a single element of a list. So this is where we see lists are read-write. So let me go away from this concatenation thing here. So if I print out L3 here, we'll see L3, we'll see 13, 14, 15. Then if I say L3 at bucket 1 is equal to a 7, and then I print out L3 again, we'll see that bucket 1 of this guy will be changed to a 7. So we can directly write to a bucket in lists where we could not do that in strings. That's where lists are read-write, where strings are read-only. If we want to change a string, we build a new string. So there's my first version of L3. There's my updated version of L3. Let's see. There's a convenience way of getting the last element of a list. I'm not a big fan of this. So, for instance, well, I kind of have to fake it. Okay, let me do it this way. So we can say L3 at bucket length L3, and then this little colon thing equals a 16. And then I can print L3. Let me show this to you first. When you add strings, the buckets from those lists change to reflect being added with the other lists. The types do not change. If I add strings to a list that only had numbers, now I have a string of numbers and I have a list of strings and numbers. So a list does not dictate that all the elements have to be the same type. Which is actually somewhat different. Let me throw that in the notes real quick. So if you've had other programming languages before, Java, C#, basically any of our high-level, strongly typed languages, we have this thing called an array, which is a collection of like type values under a single variable name. Now, this is a lot like lists. We might say a list in Python is a collection of values under a single variable name. They don't have to be of the same type. And that has to do with, I mean, that's not really a design choice. That's more of Python is a loosely typed language, so they don't have a way of forcing that. Yeah, so that's more of a side effect. So when we work with Java next semester, you'll see that we'll be doing some drills with arrays early on to kind of learn the syntax differences. And we really will be working with arrays very similarly how we work with lists. And we might say that just because a list can hold values of different types doesn't mean it typically would hold values of different types. So something like what we had up here before, where I had L4, well, here. I said L4 is equal to L2 plus L3. Something like this, while it is legal in Python, is something we probably would not do for solving most problems. Because now I have a collection of strings followed by a couple of integers. And that might not be all that useful. Remember, we're trying to solve real-life problems. Okay. So let me show you this. This is a way of adding on to the end of a list. One second. Wonder why that's not working in this. I never use that syntax anyway, so it's not necessarily a problem that it's not working, but oh, that's why. Because I can't put a direct value. I'm basically saying I want the element at the new end of it to be a list that's 16, and this will do the gluing together. So this is equivalent of me saying L3 is equal to L3 plus 16. I don't find this all that useful. Just a syntax that is supported. What you'll actually probably use, they introduce it in the next chapter, is instead of saying this, we would say L3 dot append. Let's say a 17. You want to put something onto the end, you'll append something to the end of that list. And that makes a whole lot more sense. Now keep in mind that these are just options. I would never test you over something like this. You know, sometimes you just have these like weird little syntaxes in languages that let you accomplish something you might need every now and then. If you happen to have it in your repertoire, that's fine. Otherwise, you could always just index the thing directly or concatenate it together like we just looked at, that kind of stuff. We can also remove from a certain element of the list, and that is something that is helpful. So, for instance, let's go back and I'm going to create a list of hello. So there's our string representation of a list. Now let me show you something that you could have also done in like previous assignments. I can have S is equal to hello, and then I can say I want the list version of S. You can turn S into the string into a list like that. And then let's say I want to delete L2 at bucket 1. Space. And then I'll print out L2. So this is bucket 1 of that. So my string is hello. L2 is going to be the list version of that string. I'll go ahead and prove that by printing out the list version of hello. I'll delete bucket 1 from that. I'll go ahead and print out L2, which should be HLLO now. There's my HLLO. And now I can turn it back to a string. I can say S is equal to the string version of L2, and then I can print S. Yeah, it did not turn it back into a string. There is a function to convert a list back into a string, but this guy did not do it. We'll stumble upon it later. It's probably like toString or something like that. But we do see here that S did change in terms of its contents. It's HLLO now. It's just a list, not a string. So we have a conversion tool to turn it back into a string. And this would help us in situations like, let's say we wrote a function that was to remove all vowels, for example, from a list. So I have this list L2 that is the list version of this string, hello. And I want to go through and I want to remove all the vowels from that guy. Well, what I can do is I can have another string that has vowels in it. We'll just keep it lowercase for right now. All right, and then what we'll do is we'll go through all the elements in this list, just like we would have done before for I in range 0 to the length of L2. So very similar to how we went through every element in a string. And we'll just prove that real quick. We'll print out L2 at bucket I. And that'll print out on an individual line each of our individual characters. So there's my HELLO. All right, so this should already be familiar to us. The only difference is instead of this guy being a string, it's now a list. And we're working with the length of that list. All right, now each time through, we want to ask if we are going to, if we should remove a vowel. All right, so we want to ask, is the current character we're looking at a vowel? And we can say something like, if vowels.find L2 at bucket I, if that guy is equal to, well, we want to say if it's not a vowel, or if it is a vowel, we want to remove it. So if it is a vowel, that means it's going to be greater than or equal to 0. So when I look for it in my vowels, if it gives me something that is 0 or bigger, it means it was one of these guys. That's where I found it. And if that's the case, I want to delete it from my list. So I'll delete from L2 at bucket I. Now, the problem with this, though, is I actually just changed the value. I just changed the length of L2. L2 is now smaller than it was a second ago because I just deleted the guy. So I actually would need to force this. Let me kind of show you what I mean by that. Print out L2 here. So as I was walking through here, was this a val? No. Was this a val? Yes. So now I delete that, but now my list is no longer length 5. It's now length 4. So we have to be concerned about how this range function works. And the way this range function works is it gets called one time and generates a bunch of values for I. So as this is going to run right now, I is 0. Do we remove that? No. I is 1. Do we remove that? Yes. So we'll get rid of that. Now I is 2. So we actually skipped looking at this L. And now we're looking at bucket 2. Now I is 3. Is that guy a val? Yes. So we'll remove it. Now I is off the end of it. So we're done. So this guy actually, I got to put the string back to where it originally was. I think this will be a good example. Now we walk off the end on the very last time through. So we're trying to ask if the bucket is bucket I is greater than or equal to 0, and the reality is we changed I. So what we need to do is every single time we delete something, we need to decrement I. I think this should fix it, and I'll explain why in a second. Nope, so that means that this gets called multiple times. So this range function is getting called each time through, and it's changing the value of I. So us deleting something at bucket I and then forcing I to be one smaller than it used to be so that we check it the next time does not fix anything. So this would be an example of something we probably would not want to do. We don't want to start deleting something from the collection that we're in the middle of working with. So what we might do instead is we might have an answer. Starts off as the empty collection. And then we might say if we're looking at non-vowels, then we'll go ahead and say answer is equal to answer concatenated with well, actually, we can just say answer.append. I already introduced it. So we will keep the ones that are non-vowels. So go through every element of L2. Each time through, we'll say, is the current element we're looking at a vowel? If it's not a vowel, we'll go ahead and keep it in our answer. So this guy removes vowels. Then we'll print out answer. So there's the list containing only the non-vowels. So there's an example there where just because a list is read and write, where we can change the structure of the list as we go through it, doesn't necessarily mean that we want to do that, because if we're going through every element of a list and we start removing things from that list, all of a sudden our list is now a different size than it was the last time through the loop. So that becomes a problem. All right, so those are the basic build functions for lists. we've already kind of seen, so here's our append. We've done append a couple times already. That tacks something onto the end of the list. We also have something called extend, which is kind of equivalent to us doing the concatenation thing, where we can extend a list with another list. So if we say my list.extend 412, so you would put the 4 and 12 at the end of that guy. We could have done the same thing by saying my list is equal to this guy plus this guy. It would have the same result. Now, here we have a list, 5 and 8, and we're going to insert something at position 1. And what are we inserting? A 1.7. So this allows us to specifically put a value at a space in my existing list. That could be pretty handy for some problems as well. So here's my answer. I just printed it out. So if I say answer.insert at position, it was HLL. So I'll insert at position 1, a 7. So now I'll have H7LL. There's my H7LL. So that allows us to shove a value in at a specific place in a string or in a list. All right. So again, though, that has a similar problem to what we ran into a few minutes ago. If I'm inside of a loop and I'm inserting something into a list, I am changing the size of that list. This is now bigger than it used to be. So it might make more sense to build a new list that has the stuff in it that you wanted. Similarly, we remove elements from a list. We can pop elements from, this pops from the top of the list, so this will remove the 14. Well, the top is, they actually treat it as the last element. Or we can pop from bucket 0. So this gives us a specific index. I would say don't worry about the pops right now. Remove at a specific index is going to be fairly handy for us. All right, and we're going to write our own sort in a few minutes. For right now, you're not allowed to use the built-in sort. You'll be able to use it soon, though. Similarly, we're going to reverse a list, even though you can, there's a built-in function to reverse a list. This index guy is pretty handy. This gives us the, it's kind of like find, but for lists. So this returns the index of the first item in the list with value X. That is the guy I'm searching for here. And I presume it returns a -1 otherwise. I can test that here real quick. So I'm going to say print answer.index of 7. That should give us a 1 because we just put a 7 at bucket 1. So there's our 1. But now let's look for an 8. And we know there's no 8 in there because it's H7LL. I expect this to give me a -1, which would be compatible with how find works. Oh, it doesn't. It gives me a value error. So this throws something called an exception. So I'd have to handle it as an exception. And we'll learn about that at a later point in time. It's something called a try catch to deal with that. So that actually makes index less good, in my opinion, because it doesn't allow us to quickly check to see if something is not in a set without knowing how to do a try and catch, which we will look at. But this guy is at least similar to find. All right, so now dump a bunch of these things. So let's say that we have a a list, and this guy is going to be equal to the list version, just for convenience. I'll have the numbers 0 through 9. So if I were to print out L, it's going to print out the list 0 to 9. And now I want to reverse that list. Now we already saw that I can say L dot reverse and then print L. And we get the reverse of that list. So we do have a function built into Python that permanently reverses a list. All right, so keep in mind that from this point forward, if I say L.reverse, this list is now backwards. Not backwards one time, it's backwards for good. That's different than me writing a little function takes a list in as a parameter and returns a new list that is that list in reverse. Maybe I say answer is equal to the empty list. I say for I in range, length of list minus 1, all the way down to, but not including -1, step by -1, just like we did for walking strings backwards. And we said answer.append list that bucket I. And then we return answer. This guy is not changing LST. Instead, it is building a brand new list, which is the reversed version of LST. All right, so I print out L, should be 0 to 9. Then I call reverse list on L, which does not change. So L comes in as a variable called LST. I don't actually change anything in here. Instead, I build up a brand new list and return that new list. I catch that list here. We prove we did not change L by printing out L. And then I print out my answer, which should be in reverse. There's my original. There's my proof that L did not change. And there's answer, that's that guy in reverse. Now let me show you this. Show you first. So I have my list. I print it out. Now I call reverse list perm like this. This guy takes a parameter in, and on that parameter he calls reverse. Now that's all he does. He does not return a value. Yet back here, when I printed out L, notice that L has now been permanently changed. And that's an important concept here we're going to talk about for the next few minutes. First, let me do change num. Show you kind of a similar example. So we'll say num is equal to 5. Print num. We'll call change num on num. then we'll print none. All right, so we have a variable, we have a variable. We print that variable, we print that variable. We call a function that changes that variable. We call a function that changes that variable. And then we print that variable, we print that variable. We saw up here that my list was permanently reversed. We're down here, we see that my number did not change. So here's my original list. I passed it to that function, which did not return a value, but that function reversed my list. And we saw that it had side effect. It permanently reversed my list. Whereas in this other case, I had a number, started off as 5. I passed that into a function. I changed that 5 to a 7. But once that function, and I did not return it. Once that function ended, it still had a 5. So any changes I had in there had no side effect. So that must mean that passing a list to a function is different than passing a number to a function. We have two different things. We have something called pass by value, and we have something called pass by reference. Pass by value says a copy of the value is passed to a function, and any changes made to that value within the function do not have permanent effects outside of the function. Pass by reference says a pointer, we can say memory address, to the value is passed to a function, and any changes made to that, let's say made at that memory address within the function do have permanent effects outside of the function. Numbers here we say primitive types are passed by value. Objects, lists, dictionaries are passed by reference. We have to be aware of the type of thing we're passing to a function, because if we make a change to that inside the function, like we did here, I passed something by reference here, and I made a permanent change to that in here, which then had permanent side effects outside of that function. I didn't have to do something so big as reversing it. I could have just said list at bucket 0 is equal to -7 or something like that. So I physically went to that place in memory and changed its very first element to a -7. First element used to be a 0. First element is a -7. All right, so that makes sense how that works? So, super important. Understanding how some things are passed by value and some things are passed by reference. But right now, what you could probably do, you haven't dealt with objects yet, you've read about dictionaries, but we haven't dealt with them yet. So in our world right now, the only thing that's passed by reference is a list. Everything else is passed by value. Let me show you that with strings here. Try to tack it on the end of it. So here's my I passed it to my function. I tacked a LOL on the end of it, but we see after that function, it does not have the LOL anymore. So strings are passed by value. All right, so that's a pretty important idea there, since as we're going through, we're going to be spending quite a bit of time over the next several classes. Well, actually, really the whole last 8 weeks, we're going to be working with objects, lists, and dictionaries. So we're going to be working with things that are passed by reference, things that are passed by address. So that means when we make changes to them inside of a function, those changes are permanent changes. All right. Just look at. Yeah, I really don't like that index function for our list. I would say just write your own. So you can write something like def. Maybe call this guy list find. Takes a list as a parameter, as well as the value we're looking for. Walk through our list. If list at bucket I is equivalent to what we're looking for, return I. Otherwise, return -1. So it allows us to pass in a list, pass in something we're looking for, go through the entire list, look at each individual element. We found the thing, it returns the position we found it in. We've checked everywhere, it returns a -1. So I can say print, that's my list up here called L. List find L, and what's in that list? Numbers, so I'll A. That should give me a -1. I'll look for a 7, and it should give me a 7. Oh, these are characters. I need to. There's my 7 down there. So there's a good example of sometimes if the built-in function doesn't do exactly what you want it to do, you could pretty quickly write your own little tool that does what you want it to do and accomplish the task. All right, so for Friday, I have a reading assignment up for you to get caught up with lists. We will be going through a sorting algorithm on Friday, and then probably starting to look at dictionaries as well. And hopefully I am back in the office on Friday, but stay tuned. We might have to do this again. All right. So questions, comments, concerns, bribes. All right. I will see everybody on Friday. Oh, a question popped up here. Yeah, I'll try to get better soon. Thank you. But unless I'm completely dead, we'll have class. At the very least, I can get myself out to my laptop. So.
Heck.
All right. Take care. And I'll upload the video. I recorded this.